Okay, so in this problem, they're going to test whether we understand what an equilibrium really tells us. So typically in an equilibrium problem, we only, and by typically I mean always, we only care about things that are gases or aqueous. Now notice here we have all gases. Now they could still do a Kc with concentration in it, but they've chosen in this problem to give us the Kp. So right off the bat, just for my own peace of mind, I'm going to write what my Kp expression is going to be. Remember, it's products raised to their coefficients over reactants raised to their coefficients. So if I do this, I'd write it as P CS2 times P to the fourth, and I would include this as H2 here, sorry. And again, all I'm doing, just as a gentle reminder, is that this right here becomes this right here. Then I'm going to put that all over my pressure of CH4 times the P, or the pressure of H2S. And again, if you take a look over here, for H2S we have a 2, so that means that over here we're going to have to put a 2. Now, they give us that value is equal to this right here, 1.5 times 10 to the second. So what we can do is for each of these scenarios down below here, we can solve for Q. Now, just a gentle reminder, if I wanted to, I could write my QP is exactly the same as my KP. The only difference is that my Q, I can put any numbers I want in here, whereas with my KP, all these numbers are at equilibrium and they equal this. So what we want to do is we want to find out if we just take the random numbers they've given us down here and we plug them into here, we'll get a value for our Q, and we want to compare our Q to our K. Now, just a gentle reminder, what we do is we create a number line, and whatever side our Q is on, let's say my Q is right here and my K is right here. If my K is bigger, the reaction is going to shift in this direction, and vice versa. So let's go ahead and let's plug the numbers in. I'm not going to rewrite this Q expression because I don't have a ton of space, but I'm just going to put this down here with the numbers already in them. So for this first expression right here, my Q is going to be equal to 1.65 times 5.70, all raised to the fourth, all over 5.92 times 3.82 squared. And through the magic of having already done this on paper before, that value ends up being 20. Now, we have a Q that is equal to 20. If our Q is equal to 20, and this is our actual value, 1.5 times 10 to the second. Well, what does it mean if it's 1.5 times 10 to the second? Well, it means that our products are not high enough. So if we were to actually write this out and we were to take our 1.5 and we were to slide it over lefty, largy, righty, reducey, we want to get rid of this exponent, right? So we go take our 1, 2 places. Wouldn't that give us 150 as my K? So I have 150, and here I have 20. So clearly I do not have enough product. And if you're wondering which way I do this, I'm like, well, my Q is 20, so I'm going to put my Q right over here on my number line. This is my number line, it's smaller, and my K is over here, it's bigger. So which direction are we going to shift? We're going to shift in this direction. So if we shift in this direction, what's going to happen? Well, that means that everything on this side over here is going to get smaller, and everything on this side over here is going to get bigger. So let's put that into our actual equation. So since CH4 is going to go down, it's going to go down, and these two are going to both go up. So it's really pretty simple. Once you've done a couple of these, all we're doing is we're just plugging in for Q, and then we're comparing it to our K value. Sorry for the hiccup here as I was doing this live, but again, 1.5 times 10 to the second is 150. So let's just see what these other Qs are equal to. Again, I've done these problems before, but you just have to plug in the numbers that they give us right here into our Q expression, which is up here. So, which, by the way, so this, it might even be easier right now since I have the ability to erase things out. I could just write it like this, and write that this is my Q expression and QP, because we're dealing with pressure. And then we're just going to compare that number to this number right here. So I'm going to plug in my numbers for the second one, and it's going to be 2.12 times 7.57, all raised to the fourth. And this is all over 5.45 times 2.89 squared. And in this case here, we have 1.5 times 10 to the second. And does that look familiar? Because it looks familiar to me, and that is this guy right here. So what we have is that this Q value right here is identical to our K value. So what does that mean? Well, it means that we're at equilibrium. And remember, if we're at equilibrium, why would we ever change? So every one of these right here is going to be a no change. I mean, it's kind of a freak accident if you think about the trillions and trillions of possibilities for Q, that it hit on this one. So more likely you're not going to have, if you just randomly throw things in, you're not going to have an equilibrium. But they just want to do proof of concept here. So let's try the last one here. Q, again, what are we doing? We're taking these values right here and we're plugging them back up into our Q expression up here. So what are we going to plug in right now? We're going to plug in 1.67. And notice here that I'm not putting any units in. That's because we are able to work without any units for our equilibrium expressions. So this is a 5.76 raised to the fourth, all over 5.90 and 3.79 squared. And we do the math here, we get 22. And remember, up here they told us that the value was 150 for K. So if we do our number line here, remember this is our standard number line where we have the lower numbers are over here and the higher numbers are over here. What we do is we're going to put our Q right here because it's 22 and our K right here, and which direction we're going to shift. We have to shift that way. So if we're shifting in that direction, what does that mean? Well, it means that everything if we shift this way, everything on this side is going to get smaller and everything on this side is going to get bigger, which seems a lot like what we did up here. So I'm just going to plug the values in again. That means that these two things over here, they're going to both decrease, and then these two things right over here are going to increase. Just one parting shot on this. Hopefully you realize that we did this entire problem using QP with pressures. Right? We could just as easily have done the problem with concentrations. They just happened to give us our K in terms of pressure. If they given us our K in terms of concentration, we have the ability with gases to go either way. So hopefully this has been helpful for you. Have a great day.